data link layer. So last week we talked about the physical layer. The physical layer is the wires, the stuff that we can physically grab, the stuff that the signals get sent across. The data link layer lies right above that. And that's what really kind of controls how information gets put onto the wire or put onto onto fiber or broadcast via wireless, things like that. It also deals with the layer above that, and it acts as a go-between between the two. So chapter outline, we'll talk about media access control. How do we go about putting those ones and zeros onto the wire? We'll talk about error control. If we happen to have a 1 in place of a 0 or a 0 in place of a 1, how do we deal with that? And that's what error control talks about. So we'll talk about some of the different ways of, some of the different issues that are involved with that. Detecting those errors, correcting those errors, things like that. Then we'll talk about some of the different data link protocols, several different types. We'll talk about a few of the more common ones. And then it finishes up talking about transmission efficiencies and the implications for management. So as far as the transmission efficiency, again, I'm not going to ask you for a calculation on transmission efficiency. I want you to understand what that means, what they're talking about when they say that. Okay, so the data link layer, responsible for moving messages from one device to another. It operates above the physical layer and below the network layer, so it has to do a translation. When we send a message, a web request to a web server, it goes down that network model through the network layer, gets passed to our data link layer, where our data link layer performs its various functions on that information, and then it gets passed down to the physical layer, where we're putting the 1s and 0s on the wire. Controls the way messages are sent on the media, organizes physical layer bit streams into coherent messages for the network layer. So it's doing that translation back and forth, so that the physical 1s and 0s, or the pulses on the wire, can be understood at the network layer. The major functions that happen at the data link layer are the media access control, telling the computer when it can transmit, when it's supposed to receive, how it's supposed to receive, things like that. Error control, so figuring out when there's an error in the data that it's receiving and figuring out what to do with that error. And message delineation, the different parts of those transmissions. Which is the beginning of the transmission, what's the end of the transmission, where's the data versus the control information in various packets. Control information is things like, this is the start of a message, this is the end of the message, this is the address of a message, this is the actual data of the message. So there's different parts of a message, and that's what message delineation is about, is identifying those various parts. So media access control, controlling when and what the computer transmits. It's important when one or more computer wants to send data at the same time over the same shared circuit. We have to have some kind of message so that not everybody can speak at the same time. Imagine in a room full of people, everybody wants to say something. If we don't have some kind of technique for handling that, it's pretty hard to understand each other. You ever watch the political shows on TV and you get a conservative and a liberal debating a point and they start yelling and talking over each other and you can't understand anything? That's because they need to do a better job at media access control. Two common approaches for media access control is either controlled access and contention-based access. We're going to talk about what each one of those means here in just a second and what the differences are between the two. For the most part, we tend to deal with, at least in the local area network environment, with contention-based. Ethernet happens to be a contention-based protocol, and so that's what we end up using. So controlling access to a shared resource acts like a stoplight. Stoplight, imagine a highway where you have to get onto the highway. You have to find an open spot on the highway as you're entering an on-ramp. You can't just jump right out there. If you do, especially if you're on the Metroplex, you're probably going to get in a wreck. So controlling access to getting onto that highway involves identifying a spot that you could pull into and getting up to speed so that you can do it safely. So it determines which circuits have access to, commonly used by mainframes or front-end processor, determines which circuits have access to mainframe at a given time. It's also used by some LAN protocols, token ring and FDDI. It's an approach where basically you don't have a right to just get on. You have to get on with certain, with the authorization of some kind of controlling device. With respect to token ring, it's a token. So we'll talk about that a little bit more here in just a second. A couple of the major access methods, X on, X off, and polling. Polling is the most common. Polling involves transmitting it to a client only if asked to and or permitted. So the client stores information to be transmitted. The server is periodically going to poll the various clients that happen to be on that network. It's going to poll a particular client. Does that client have a message to be broadcast? If it does, then it responds and says, okay, I've got this message, and it shares it. If not, the server moves on to the next computer. So if no data is sent, the client responds negatively, and the server asks the next client. There's a couple of different types of polling: roll call polling versus hub polling or token passing. With roll call polling, it's basically just going to go with the very first one. It's going to go check the very first computer. Do you have a message to share? If you do, great. It's going to handle that message. Then it's going to go check with the next one. Then it's going to go check with the next one. And you have the ability to prioritize certain clients in that environment. Let's say you've got a CEO over here that you really want to appease and make happy. In an ideal situation, you wouldn't do that. You would hopefully prioritize the computers that actually make money for the company. But if you really wanted to appease the CEO, make sure he has real good response time, you can make sure that the server checks A, then goes and checks B, then comes back and checks A, and then goes and checks C, and then goes back and checks A. So you can really kind of manipulate how the priority of various clients that are involved if you want. So the downside with this is it involves waiting. Why? Because if you poll A, that means B, C, D, and E are sitting there and waiting. They're not doing anything. They may all have a message to send, but they can't because the server's dealing with client A right now. Same thing when it moves to B. It moves to B, it can't deal with any of the other clients. So there is a little bit of a delay in responding to each one of those clients. You also have to periodically have a timer that it times as it's checking with the various ones, so it doesn't get hung up with one particular client. It has to check with that client. After so much time, it times out and moves on to the next client to check for it. With token passing or hub polling, basically you don't need a server in that type of environment. This is what you see in token ring, where you have literally a ring of computers that are connected. And the way this works is the network cards are token ring network cards, and they pass what they call a token. And that token passes from A to B to C to D. If a particular client, say E, didn't have anything, it just passes that token on to A. A happens to have a message. What it does is it attaches that message to the token and sends the token on its way to whatever client that happens to be addressed. Once it gets to the receiving end, wherever it's being sent to D, it gets to D, it removes the message from the token, sends the token on its way, and is able to read the message. So the downside on something like that, if you end up with a break in the wire, you can't pass messages anymore.
Oh, cool.
They spare no expense on the slides. Contention is a different approach. Rather than controlling access to the media and saying you have to raise your hand before you speak, or you have to grab a token, or anything like that, contention-based methods basically say, yell out your answer. It doesn't matter. It's a small enough class. We're not going to really be interrupting each other that much. We can just speak up as we need to. The downside with that is collisions do occur. Same thing in speech. You ever had that moment where you're talking to a friend and you both start to say something at the same time? Collisions occur. What do you do? Well, basically, you kind of stop, say, I'm sorry, go ahead, or vice versa. And one of you finishes your statement, and the other one shares theirs. So we kind of have a protocol for handling that. Contention-based methods do as well, and we'll get to that here in just a second. With contention-based approaches, you need to determine which computer is allowed to transmit first after the collision. That's done basically by a random number generator that's built into each network card. So after a collision occurs, the network card will issue a jamming signal that basically jams the network for just a second, tells all the network cards, hey, be quiet for just a second, we're trying to send a signal. It'll wait a random amount of time, and then it'll try to retransmit. And if another collision occurs, it'll do it again, but it just continues through that process. Eventually, it happens so quickly, eventually the message will get through. As it says, commonly used in Ethernet LANs, can be problematic in heavy usage networks. Why? This is why. If you've got a small enough network, you want a contention-based approach, because it's pretty easy for a small group of people to get together, talk to each other without having to go through some formal process of raising hands and identifying speakers. That slows things up in a small environment. But if we get into a big classroom with a lot of students, we have to all talk to each other and share ideas. If we did that, it could get pretty chaotic pretty quickly. So you have to have some kind of approach where you raise hands and you identify people to share their points. It's the same thing that's occurring here. So once you get up to around 20 computers on the same segment, it's about where your break-even point. So for smaller networks, you can get faster response times with contention-based networks. It takes longer for controlled access-based networks. But once you get up to a large enough number of units, those controlled access methods tend to work better. So it sort of depends on your environment that you're working in. Once you get up to those a high number of users or a lot of traffic in contention-based networks, you start to end up with so many collisions because there's so many different computers trying to talk at the same time. You have to retransmit a lot of data, and that just exacerbates the problem. Any questions so far? Okay. So let's say there is a problem. How do we handle that? We've got a control for those types of errors. It's referred to as an error. And they can be caused by a variety of things. Network errors, human errors. Essentially, we end up with a couple of different categories of network errors, either corrupted data or missing data. As far as some of the types of things that you might see is a change in a bit value, problems caused by network hardware, software, etc. An error rate is a bit error in n bits transmitted. For example, 1 out of 500 bits. That's a pretty good error rate if we only have 1 out of 500,000 bits. That doesn't tend to happen very often, though. Instead of something like that happening, what we tend to see is a burst of errors. Why? Because if you have a spike in the line, say a lightning strike, or you have a piece of equipment that goes down, what it does is it affects a bunch of bits all in a row. The rest of the time, our network really runs pretty good in general. Networks tend to run pretty good. As far as the sources for some of those errors, tends to be more common on electrical media. Remember last week we talked about fiber. That was one of the appealing things to fiber, is it doesn't suffer from some of the errors that you might run into with electromagnetic media. They're light pulses, so if electromagnetic interference doesn't cause a problem with it. Undesirable electrical signals caused in a lot of cases by equipment or natural disturbances, lightning strikes, failing equipment, heavy motors, big motors sometimes will cause some of those problems. And it'll cause the circuit to degrade. How does that result in errors? Well, it results in extra bits. So you might have a 9-bit byte. If you remember any of that stuff, there's supposed to be 8 bits in a byte. So you might end up with an extra bit. You might end up with flipped bits. So a 1 ends up being a 0, or a 0 ends up being a 1. It's not the same message. That's going to cause a problem. And then missing bits. So kind of the reverse of extra bits. You've got a 7-bit byte instead of an 8-bit byte. So how do we deal with those errors? What do we do about it? Well, the first thing we want to try to do is prevent it. Because if we can prevent it, then we don't have to retransmit anything. We don't have to do any kind of error correction on the receiving end. So there's a variety of different things we can do if we end up with an error, but ideally we can prevent those errors from occurring in the first place. Regardless of how much we try, though, there are going to be errors. There are just too many things that occur in nature that we can't really prevent it. So we have to have the ability to then detect errors, because we've got to know if a data has flipped a bit or something like that. If not, we're not going to get the information that we want. We may download some huge file, but one little bit in the wrong place, and it's not going to work. And then ultimately our issue is getting back to correction, getting back to the file that's supposed to be there, the ones and zeros that are supposed to be there. So they kind of give you some sources of errors and what to do to prevent it. They kind of left line outages blank, and I'm not really sure why. They talk about faulty equipment, storms, and accidents. They could have put UPSs, for example, up there, uninterruptible power supplies. They could have put redundant cables, for example, redundant power supplies, redundant network connections, things like that to try to prevent line outages. But then they talk about white noise, impulse noise, crosstalk, various things, various causes of those things, and various things to prevent it. In a lot of cases, you'll see a lot of redundancy on the prevention side of things. A lot of them are just very basic common sense things to do if you've been doing this for a while. Things like making sure your cables are away from electrical, that your data cables are away from electrical cables. They're not around fluorescent lights. Making sure that the shielding on them isn't cracked, that you're not splicing the wires back too far. Things like that. So, as far as error detection, I wish they had done this. You've got several different things going on. So, on the sending side, we send a packet across a wire. What you can do is you can end up doing some kind of calculation, to create an error detection value. And that's kind of a generic term for some of the other subterms that we'll talk about here in just a second. But you end up generating what's referred to as an error detection value based on your data. It's usually a one-way hash. It gives you a number based on your packet. It's going to attach that to your data, and then it gets sent across the wire. On the receiving end, it performs the exact same calculation. It looks at the data, it performs that same calculation, and comes up with a number. If the number is the same, then there's no error in the transmission. The data is good. If they're not the same number, then there's a problem. Now, different types of error detection values. There's some of the common ones are parity checks, checksum, and cyclical redundancy check. That's in order of how effective they are. So least effective, more effective, and most effective. About 50% up to almost 100%. So parity checking, oldest and simplest, a single bit is added to each character. So if we're using even parity, then the number of ones remains even. We look at our number of bits. If we've already got an even number of bits set to 1, then we don't do anything with the last bit. If there are odd number of bits, we're still using even parity. But if there's an odd number of bits set to 1, the last bit we're going to change to a 1 so that we have an even number of bits set to 1. Odd is just the opposite. We want to make sure the number of ones is odd. So the receiving end recalculates the parity bit. If one bit has been transmitted in error, the received parity bit will differ from the recalculated one. So what's the problem with that? What happens if you have 2 bits that are flipped? Now that check says it's okay. So that's the problem with it. So it only catches about 50% of the errors. So using 7-bit ASCII, you might end up with a code like that. If we're using even parity, we've got 1, 2, 3, 4. We've got 4 ones. So we don't add, to the end of that, we don't add a parity bit. Or we add a parity bit, we just don't add a 1 to it. On the receiving end, we end up checking that, assuming we get this message, we calculate that out, it's a 0, they're the same. So it's, according to us, it's a good message, assuming we haven't had more than one flip. Odd parity, again, is the same thing. We calculate the ones, 1, 2, 3, 4. We've got an even number. We're using odd parity. So now we're going to add a 1 to make it odd parity. So it's just a choice that the type of parity that we want to use, we select. And then that, based on that, is how the bits are set. Checksum's a little bit better, about 95% effective. Instead of adding a single bit, we're adding an entire byte. But the concept is basically the same. It's just a little bit more complicated calculation. Add decimal values to each character in the message. Divide the sum by 255. The remainder of the checksum. The remainder is the checksum value. So again, I'm not going to ask you to do the calculation, but I want you to know basically what's going on. That it's looking at your message, it's generating based on a formula, in this case this formula, to come up with a number that it then checks that against on the receiving end. If those numbers are the same, then the message is good. If not, then it's not good. Tends to be pretty good. Oops, I clicked ahead, didn't I? Yeah. Tends to be pretty good for the most part, but again, it's 95% effective. What about that other 5%? And that's where CRC comes in. Can get up to 100% of errors if the number of errors is less than or equal to the size of R, with R being the remainder, and it explains this over here. Essentially, it's a more complicated formula, and it just basically goes through this process of calculating that hash on the message and providing that along with it. So we've detected that there's an error. What do we do with that? Well, the easiest thing to do is to retransmit the message, right? I mean, we get an error, we can just retransmit the message. If somebody says something to you and you didn't hear them, you say, excuse me, pardon me, I didn't hear you. What'd you say again? And they retransmit the message. They repeat it, you hear it, hopefully, and you kind of move on. Obviously, that's a pretty simple approach, but it's pretty effective. It's pretty efficient for the most part. It's the least expensive. It's very commonly used. Corrected by retransmission of the data, etc., etc., etc. It uses a process called automatic repeat request, or ARC, and we'll talk about that here in just a second. There's kind of like a few graphs that kind of illustrate that. The other technique is forward error correction. That's where basically where you're able to, instead of retransmitting the message, the receiving end is able to take that garbled message and regenerate the original message. And again, I'm not going to get into the specifics of it, but there's a few downsides to it, but there's some plus sides to that as well. We'll get to that in just a second. So, on retransmitting, how do we do that? Well, there's a couple of different ones. There's a stop and wait ARQ and continuous ARQ. With the stop and wait approach, what happens is the message gets sent. The receiving end does its calculation, whether it's CRC or a parity check, whichever error checking method that we pick. It performs that check. If everything's okay, it sends back an acknowledgement. It says, I got this message. You can go ahead and transmit the next message. And it does that back and forth. It stops and waits until the sender stops and waits until it gets that acknowledgement back. If it gets a NAC back, a negative acknowledgement, that says, oh, there's a problem with that. The parity bit was flipped, or CRC, it didn't pass CRC check. We need to retransmit that same packet again. So that's the stop and wait approach. Continuous ARQ takes a little bit different approach. It says, our networks are pretty good. We don't have a lot of errors in our networks anymore. Most of the data that we send gets there in one piece. So instead of spending all this time waiting for acknowledgments or ACKs and NACs, we're going to send a bunch of messages, maybe not a bunch, 3 or 4 or 5 messages, and then we'll wait for an ACK. And we're going to keep doing that because we can process more data that way more quickly. So we'll try that. So stop and wait, like I said, it sends that very first packet, no error detected, so it's going to send back that ACK. I got it, fine, everything's fine with that message. We send the next packet, it says, wait a minute, it didn't pass that CRC check. I want to send back a negative acknowledgement. I didn't get that message retransmitted. And so then it has to retransmit that same packet. The downside is you're wasting a little bit of bandwidth there. You're wasting some of that time on sending this negative one-for-one and having to wait for this NAC to go back and then having to retransmit that same data. So that's why prevention becomes important. You want to prevent errors in the first place if you can. Continuous ARQ uses what they refer to as a sliding window. I think there's a slide here, a few slides that kind of illustrate the sliding window part of it. But with a continuous ARQ, we're going to send packet A, and we're going to send packet B. We're just going to send several different packets before we decide to say, wait a minute, I need to get an ACK back. Well, on this very first one, it sends the first 2. On the third cycle, it gets an ACK back for the very first packet. That was okay, so no problem. It continues sending. It sends packet C. There's an error there, but we don't worry about that just yet. We're going to continue to send. finally gets an ACK back for B. It sends D. It finally receives an ACK back for C. It says, hey, there was a problem with that packet you passed to me a few packets ago. You need to retransmit that, so it does. And so it's a way to get more of the data to the receiver more quickly. The problem with that approach is, if you ever, somebody been talking to you and they're giving you so much information so quickly, maybe this class, I hope not, but they're giving you so much information so quickly you can't process it. You can't take notes quick enough, you can't think it through quick enough. That's an issue of flow control. There's flow control has two sides to it. There's the receiving side that says I can accept information so quickly. There's the sending side that says I can provide information so quickly. And while we have some flexibility with respect to being individuals and being able to adjust to within reason our ability to control the flow of information, computers have to be pretty specific about how much data they can send and receive together. So with stop and wait ARQ, it's not really a problem because we send one packet, we wait for that ACK or NACK, and that's it. So flow control is not a big deal with stop and wait. But when it comes to continuous ARQ, they have to agree on the size of that sliding window. How many packets can you send out before you have to wait for that ACK? 2, 3, 10, 20? It's an issue. So the flow control example they throw out here. We start out with a window size of 4 is what the sender is going to say. So it immediately sends out those very first 4 packets, 0 through 3. On the receiving side, it immediately sends back an ACK. Well, that's going to free up 1 packet. So that window slides down, and it can now send 4. It gets an ACK for 4. Actually, it looks here that they didn't really denote it very well, but I'm assuming it's 1 through 4 right there. So now that sliding window can slide all the way down and do 5, 6, 7, and 8 because the window size is 4. It has to receive an ACK back before it will transmit the next one. It won't transmit the next one until it receives an ACK for something. At that point, the receiving side says, you know what? I'm getting too much data too quick. I need to adjust, and this is done automatically. It's not something you as a user sets up. But on the receiving side, it says, wait a minute, I'm getting too much data too quickly. I can't process this much information that quickly. So it sends back information to say, hey, I want the window size to be set to 2 so I can control that. I can handle that information better. So it sends an ACK back for 7. Now our sliding window drops down to just 2 bits, or two frames. Any questions so far? Okay. So forward error correction. It'd be nice to not have to retransmit that data. And there are situations where you can't afford to. They talk about one-way transmissions where retransmission is not possible. I can't think of an example off the top of my head for that, but sure there are certain situations. Transmission times are very long, such as in a satellite transmission. Certainly, missions to the moon, things like that, where the transmissions take a significant amount of time. You don't really have a lot of opportunity to retransmit damaged messages. So it says in this situation, relatively insignificant cost of forward error correction. That the problem with forward error correction is it requires quite a bit more data to be sent with the original message. The plus side of it, usually 50 to 100% of the data. The plus side is you don't have to retransmit the data. If there's a problem with it, it can regenerate the original message. So it requires that extra corrective information to be sent along with the data. So then they actually go through an example of how they go about doing that. And again, I don't want to get into the specifics of that. I think it's beyond the scope of the class, but needless to say that it basically takes a matrix approach to be able to regenerate that original message with that extra error correction information. And Okay, so let's start to try to relate that to what you normally hear when we start talking about the data link layer and some of those data link protocols. First off, we can classify those data link protocols as either being asynchronous or synchronous. And that's just a reference to how we're going to sync up our messages, whether or not we're going to have to create a connection between the sender and the receiver, or if we're just, for synchronous ones, transmissions, or whether we can just broadcast messages, and whenever we're ready, we send it, the other side gets it, or it doesn't, we don't worry about that, which would be asynchronous. Some of the differences between the two, they differ by message delineation. So where does the beginning of a message begin, end? Where are the different components within a message? For example, the addresses, the information about parity, the information about the actual data, the payload itself that we're interested in. The frame length, so how much data can we actually put in that frame, and the frame field structure that I was just talking about a second ago. So with an asynchronous transmission, we're going to have some kind of start bit for the receiver separating the character and for synchronization. So our normal or idle state may be at positive 3 volts. That represents a 1. When we're ready to start a transmission, we drop it down to 0. Then we transmit exactly 7 bits of data, our actual data that we're trying to transmit. We transmit our parity bit, and we transmit our stop bit. Now, I think if you think about this in terms of sending data across the wire, you can see that it's really critical that it always stays at positive 3 volts, and that we only, when we're not using it, when we're not transmitting data, and that we only use this number of bits for each transmission. If we add a 1 or we add a 0 some in there, now all of a sudden we don't know where the parity bit is, we don't know where the stop bit is anymore. It becomes a problem. So we have these distinct units of bits that we have to transmit. Asynchronous file transfers used on point-to-point asynchronous circuits, phone lines via modems. Think about modems when you're sending data. You're sending data or you're not. It's not a case where it tries to keep that connection alive or anything like that. Sometimes called a start and stop transmission, because we start it right here. Once we've transmitted our data, we're done. We can wait until there's a need. A user clicks on a link, for example. Now we start transmitting and receiving again. Designed to transmit error-free data. Groups data into blocks to be transmitted rather than sending character by character. And that gives you a couple of examples there. So it talks about the structure of the frame here. I'm not that worried about you knowing the exact structure of frames, but I do want you to kind of get used to looking at some of the common components about it. Obviously, your message, for example, the data, the payload itself, that's the information you're really interested in. If you were attaching a file to an email, all that header information about the email is important, because without it, the email doesn't get where it's supposed to go. But what you're really interested in is that Word document, or the content, the information that you wrote in that email. So that's the payload, and that's what you're really interested in. But this other information, the start, for example, packet numbers, checksum, that's important information. So I want you to kind of focus on the general structures of packets, not necessarily the specifics of any particular one. Synchronous transmission, data sent in a large block. So rather than sending those individual characters, we're going to transmit a larger block called a frame or a packet, typically around 1,000 characters or bytes long. A packet's going to include addressing information, especially helpful in multi-point circuits. Let's see. Include series and characters. Synchronous transmission protocol categories. Bit-oriented protocols, byte count protocols, and byte-oriented protocols. In the next few slides, go over each one of those. So SDLC is a bit-oriented protocol developed by IBM and uses a controlled media access protocol. The way it starts to synchronize between the sending side and the receiving side is it starts off with this flag bit right here, which is a 0, then 5 or 6 ones, and then a 0. And it ends with the same thing. It's got address bits, so where it's going to. It uses control bits for telling whether or not the packet is full of information, or whether or not it's got control information like flow control or error information. The data itself, CRC check, so to determine whether or not there's an error in transmission. And then on the closing flag, on the closing end, say this is the end of our packet. Why? Because our message length is not variable. If you remember our packet earlier, we have to transmit exactly 7 bits. And then we've got our CRC check and then our closing flag. With this, so our frame size, our data size is always exactly the same with asynchronous. With synchronous, though, we can have a different size packet. It's not a problem. We can have a bigger one or a smaller one because we're noting when the beginning, when the end is. There's a problem with it called the transparency problem is what if somewhere here in our data that's being transmitted, we have a string of those zeros and ones that's exactly the same. That creates a problem because now all of a sudden we've identified this ending flag somewhere over in here. Well, now we can't do our check, our CRC check, and all this data back here is just garbage. So the solution to that is what they call bit stuffing, inserting a 0 in here, where basically it looks for 5 zeros, or 5 ones, and if the next one's a 0, it removes it. It's the stuffed bit. If it's 1 0, that's the end of the frame marker, so it knows that's the real end of the frame. If it's 1 1, then there's an error because there can't be 7 ones, continuous ones in the data. The problem is that it increases the complexity. It makes it's not quite as simple to implement as the other method, or as it originally proposed. A different approach is HDLC. Very similar. The difference is longer address and control fields. So you can have a larger sliding window size. It doesn't have those problems because of the longer address field. I'm not concerned all that much about all of this because most of the time you're not going to be dealing with most of these protocols. Now, Ethernet is the one you will be dealing with the vast majority of the time. So that's what we usually want to focus on, where you want to spend most of your time. That's pretty much the standard for local area networks. And you're starting to see it more and more in metropolitan area network environments and even WAN environments because of the speed increases that you're starting to see. It was originally developed by Digital. Intel came along with, it was originally developed by Xerox. Digital and Intel came along and kind of advanced it to the point of you end up with what's referred to by some as the DIX Ethernet, DIX. There's actually different standards of Ethernet, and while they're very similar, that frame structure that we were talking about, where the addresses are, for example, the size of the fields, the size of the data, those are different depending on the specific Ethernet standard that you're talking about. So they're not necessarily compatible, though for the most part they do tend to be able to negotiate with each other and speak with each other. Now, Ethernet's a contention-based media access control. So what did we say contention-based was earlier? What was the method for talking? It was speak up now, just blurt it out, and we'll deal with any collisions later. So rather than raising your hand or anything like that, speak up. It's a byte count data link layer protocol, and it doesn't have the transparency problem. It uses a field containing the number of bytes. That's how it avoids that issue. So right here, it's got a length in bytes. So now, instead of having to worry about that number over here of 0, 1, 1, 1, 1, 1, 1, 0, it tells you exactly how long it's going to be right there. So it knows if it happens to run into that flag there, it's not a problem, because it knows where that message is going to end based on this information. Error correction with Ethernet is optional. You've got a slot for it, but you don't necessarily have to use it. So the basic structure of the frame: destination address, where it's going to, the source address, where it's coming from. So when you see CSI and stuff like that, and they talk about being able to track things down to specific machines, they look at IP addresses and they look at MAC addresses. These are some of the information that they're gathering about transmissions, so that they can narrow it down. LLC control, snap control, the actual message itself, and then the error correction, or not correction, but error detection there at the end. A point-to-point protocol is a protocol that oftentimes gets used between an endpoint communication and a single other endpoint communication. So a lot of times when you're dialing up to if you're using dial-up networking, you'll end up having not only TCP/IP protocols installed on your computer, you'll also have a point-to-point protocol installed on your computer. That's what establishes the connection from your particular computer to the ISP. Then within those point-to-point protocol transmissions, you're transmitting your TCP/IP packet information. Designed for mainly for point-to-point phone line, can be used for multi-point lines as well. And again, you should be able to look at this packet here and start to say there's a lot of similarities that we just saw with Ethernet. You're seeing flags, for example. You're seeing addresses, control bytes. In this particular case, you're seeing a protocol, and we'll talk about that a little bit more later. I think there's another slide comes up here in a little bit that talks about that. Your message that you're trying to transmit, your error checking there, and then a flag there at the end. So now they kind of give you a comparison of all your various data link protocols and how they compare to each other. The one, again, that I'd want you to focus on would be Ethernet. It's down here at the bottom. Uses a 32-bit CRC check, so it does a very good job of detecting errors. So worst case scenario, if you remember from that slide that we looked at earlier, it was like 99.9998%. That was worst case scenario of it missing an error. So chances are really good that if an error gets produced, that it's going to be able to detect it, that Ethernet's going to be able to detect it. Now, Ethernet does use a stop and wait ARQ. What was that? What does that mean? What did we say that meant earlier?
It's a delay.
Say again?
There's a delay, like you gotta wait until the next customer.
So we send out a message, we wait till we get an ACK back. Then we'll send out the next message, and we wait till we get an ACK. So it's kind of slower, but we don't run into any of those, hey, I'm getting lost. We don't have an issue of flow control like we do with a sliding window. It also uses a contention-based access. What did we mean by that? Contention-based as opposed to controlled access. Controlled access, we had to have some kind of mechanism to say you can speak now, you can contribute, you can put your message on the wire versus you can't. So with control-based, we had to have a token of some kind. We had to have some kind of server or token that was keeping track of messages, that was keeping track of whose turn it was to speak. With contention-based, you just speak, and hopefully nobody else is speaking. If somebody else is, then you have the collision, you have to retransmit. The last part of the chapter talks about transmission efficiency. Ideally, we don't have to transmit all that extra stuff that we're sending along in that packet. Remember that the address part of the packet, the error correction, all that type of stuff? That's overhead. And it's necessary because we want those packets to reach their destination. We want them to reach their destination intact, so they're being received as they're being transmitted. But at the same time, what we're really interested in is the payload, the actual data itself. So the more data that we send and the less overhead that we send, the more efficient our transmissions are. But that overhead is necessary. So we have to be careful with how much overhead we use. So we want to move as many bits as possible with minimum errors, higher efficiency, lower cost. Factors affecting network efficiencies, characteristics of the circuit, so error rate and speed. So are we using unshielded twisted pair wire in an environment that's probably not the best for that type of wiring? Perhaps shielded twisted pair or fiber would be better. So the characteristics of the circuit can cause it. The speed of the equipment and error control techniques that we're using, those are some of the possibilities. Maybe our wiring is going too close to a motor or something like that. The protocols used as well can be a factor. So kind of a general way of looking at the calculation is the total number of information bits to be transmitted over the total number of bits. So that total number of bits is not only our data bits, but also that the overhead bits. So with asynchronous transmission, we're transmitting 7 bits of ASCII data. We've got 1 parity bit, 1 stop bit, and 1 start bit. So we've got 3 bits of overhead. 3 plus 7 is 10. Our actual data is 7 bits, so 7 over 10, 70% efficiency. Maybe that's good, maybe that's bad. I don't know. Relative to some of these other techniques, it's not very good. But that's how you can make a better comparison. So that's more like what you might see with a modem. 56K modem, you're only getting effectively 39.2K out of it. Now with SDLC transmissions, assuming 100 information characters, so about 800 bits, or you got 2 flags, or 16 bits, the address, which is 8 bits, control, which is 8 bits, CRC is 32 bits, all of that is overhead. But your message size is quite a bit bigger. So, that's not right. Yeah, I don't know what that should be. Maybe it's 64 over. Yeah, that's not right. But they're whatever they're coming in, it should be the total of all those numbers for your denominator, and then 800 over that. But they're coming up with a much higher transmission efficiency for that. If we were using a 56K modem with that kind of efficiency, you see our speed goes up to 51.9 versus the 39.2. So the message that you should take away from that, the bigger the message length, the higher the efficiency. But there is a problem with that. Why don't we just make the message field as big as we possibly can, so we don't have to break them up into smaller packets? The problem with that is when we have one of those errors, we'd have to retransmit. That takes up more of our capacity. So we have to kind of reach a balance between the size of our actual data and the number of errors that we're going to see on our network. So really what we want to focus on is throughput, not really our efficiency, but really our throughput, because we want to make sure we're getting as much of our actual data through as we can. So more accurate definition of efficiency is throughput, the total number of information bits received per second. And it takes into account the overhead bits and the need to retransmit those packets if an error should occur. It's not, as you might guess, it's not particularly easy to calculate, but you can kind of look at a representation of what it might look at. You see a curve here where your throughput is going to increase, increase, and increase as your packet size gets bigger up until a point. Because these small packets have really low efficiency. Why? Because you've got a lot of overhead to a little bit of data. So as that packet size gets bigger, our data part of the packet gets bigger and bigger and bigger, we become more and more efficient. To the point that we start to see diminishing returns. But now all of a sudden when we have an error, our packet is big enough now, we're having to retransmit it, that's tying up additional bandwidth. So there is kind of a sweet spot up here, an optimum packet size that says we want our data size to be a certain size in order to be able to balance that need for retransmission versus the number of errors that we're going to see. That calculation, and again, I'm not going to ask you to specifically do the calculation, but the number of information bits times the probability of successful transmission over the time it takes to transmit these bits plus the propagation delay. So what does all of this mean to management? Well, provide a few widely used data link layer protocols for all networks. Why? For a variety of reasons. One, the more different data link protocols that you have running on a network, the wider variety of hardware you're going to have to be able to support it. So instead of simply having Ethernet cards throughout your network, you've now got to have Ethernet cards, you've got to have token ring cards, you've got to have network devices that are able to interpret the different signals that are generated by those different standards. So you're going to have increased costs not only in the equipment, because you can't buy in bulk, also going to have more expensive employees. Why? Because usually when an employee is really good at one particular technology, that's their thing. There tend to be more people that know that one technology. To be able to get somebody that understands 2 different technologies, 3 different technologies, the more expertise they have in these various fields, the more expensive those personnel are going to be. So you drive up some of your costs as far as your personnel as well. If you focus on something like Ethernet, definitely a standard. For the most part, it's backwards compatible. If you have gigabit Ethernet, you're still able to utilize 10 meg network cards. If you happen to have a machine that still has one, you don't have to replace it. It's just not going to talk at the 10 gig speed. So you can really focus on some of that cheaper off-the-shelf equipment to help keep costs down. That's it for that chapter. It's a pretty good chapter. Parts of it are a little bit wordy with some of the calculations, but again, I don't expect you to do the calculations, but I do kind of expect you to know what that calculation, the heart of that calculation is saying. When we talk about transmission efficiency, that it's about the relationship between that overhead versus the data that's actually being transmitted. So any questions over chapter 4?